Welcome here, and my name is Jussi Pakkanen, and I'm the lead developer of the Meson build system. And I'm here to talk about how you design a build system and a dependency manager, specifically the latter, and how hard can such a thing really be. But let's start from actual first principles. So what is a dependency? That might be a bit too much of a first principle, so let's do something more concrete. So when people say, okay, I have this dependency, I use this dependency, what is that they mean? And different people have different meanings for this, and it's usually not set out, like what do we actually mean by this? So what would be a good definition of using a dependency? So I thought about this for a while, and came up with this. So given that you have two separate pieces of software, A and B, and then we want to use those two together in some way to achieve functionality C, which combines these two with minimal amount of effort, and preferably none at all, where you could just take, and then you're done. And this is usually what like the thing that people actually want when they say that they want to like do something with dependencies. Right. So given that, so let's look at how dependency management is done, because there are a lot of different ways that you can do this. The first approach is, of course, no dependencies. So whenever you need new functionality, you write it from scratch, and you get like the artisanal small batch quality of code. And this actually works for many projects. Like if you are doing something like you want to learn something new, this is typically what you use, because like implementing the thing from scratch is the thing that's interesting. And then there are like things that are very small, like very small firmware things or something like that. And if you don't need something very complicated, you need something very specific, writing it yourself, that might be a good idea. So this is an option. Then there's the copy-paste option. So whenever you need some sort of functionality, you find an implementation of that, and then you copy-paste it inside of your own project. There was a bit of research done some years ago, I think, where they tried to see how many different implementations of something like SHA-1 exist in the world, because using OpenSSL is difficult, so they just copy the thing from there. And they're like, inside of Debian, there's like 1,000 different copies of that, which is great for security. But again, for some use cases, this is actually a reasonable thing to do. But neither of these two are very interesting from like a dependency management perspective, because you do it once and then you don't touch that. So then the next one is system dependencies. This is what you know from typically from Linux distributions, is that you have your dependencies, which are installed on the system, and then you use them. Package config is the most common way to use this. Some build systems also have their own like CMake has CMake modules, which you can install, which then tell, okay, if you try to find a thing from the system, this is how you would do it. And this was invented, I think, in the early 90s. It's still being used. It's like, when it works, it's really nice, because you've farmed out the maintenance work to other people, which is always the thing you want to do. But again, not suitable for all use cases. Another thing, which is called vendoring, is that you take the external project, whatever it might be, inside of your own project. Then you adapt it to whatever thing is that you need it to do. Typically, this means rewriting the build system to do the thing that you want. Those who know Google's Bazel, or like the Blaze, the internal thing that they do, this is basically what they do. Is like find an open source thing, copy it inside, change the thing to build with Bazel, and then you just use that. And again, this works for many different use cases. And there are third-party package managers which you can use. Typically some sort of curated collection, different kind of dependencies. Conan is I think the most popular one at the time, for C++ at least. There's VC Package, which is made by Microsoft. And then there are a bunch of other ones as well. So this is basically like copying the system dependency model, but provided by a third-party thing rather than by the operating system provider. And then there are language-specific package managers as well, which is much like the same, but it's specific to the way a single language works. And the D programming language has a thing called dub, where they have their own curated thing, and you can download the libraries and use them, all of that. And further, then there is this thing called language-specific source collators. I don't think this is a term I made up, so I don't know if there's like an actual term for this. But basically, you download and build all of your dependencies from source always, and you build them with the same build system. And Rust's cargo is a common example of this. I think NPM does roughly this, but I haven't done any front end, so the details of those are a bit hazy. Right, so these are the major ones that I could think of. So then the obvious question is that if you have C and C++ code, which one of these should you use? And this is a source of many interesting debates on the internet. And in bars, typically when back when conferences were a thing, like afterwards. But this is the wrong question. And it's approaching the problem from the incorrect angle, because it's ignoring the existence of all the things that we already have. It's like, if you would be able to do a thing from scratch where you ignore the past, then okay, you could do that. You would just need to get everyone else to agree to do it with you, but you could do that. So this is not really a feasible thing to do if you have an established large thing that runs, for example, the world. So what would the design principles be if you wanted to create a general purpose dependency system from scratch? And let's see. So design principle 1. You have to start from somewhere. Let's start from 1. You have to support all of these different things. All of them, even mixtures of them within a single project. That's messy, but the world is messy. And if you want to make headroads in the messy world, you have to be able to handle all of that complexity. Because if you say all of these things have their own users, if you tell this group of people, no, you can't do that, all of you have to move to this other camp, it's going to be like a tricky sell. Okay, so then let's look at somewhere else. If you have more than 2 pieces of software at the same time, then what happens? What sort of dependency change do you get up? So this is the most typical one. So this is what we mentioned earlier. You have your thing C, and it uses B, and it uses A, and then everything is fine. But you can arrange these boxes in a different order. So suppose you have this. So you have C, which uses B, which also internally uses A. So it's just an implementation detail that there is an A, but from a C perspective, the only thing is B. But then you can also have this, where you have C, where B uses A as a hidden internal thing, but C also uses A for some other purpose. If you have something like zlib, this is quite common because lots of libraries depend on that, but other people also depend on it directly. Okay, but what if you have even more stuff? So what if you have D, and now you have D, which uses C and B, and they both use A. Now you have an ODR violation, because there's no telling that these are the same thing. If you compile if they're different versions, you have an ODR violation. If you compile them in different flags, you have an ODR violation, and so on. And how would you even know that this is a thing, other than the fact that you get a call somewhere at 2 a.m. when things don't work? So from this, we can find the second design principle, which is a bit contentious, is that the dependency managed system, it must prevent multiple ways of getting the same dependency. And this must be done automatically. If a human being has to in any way inspect the dependency graph of your things to find that, are we doing the right thing, that doesn't scale. So it has to be automatic and it has to work. And the system must say that you have multiple versions of the same thing, I'm not going to work. Now, when I talk about this, usually there's some guy who always says like, I have a special case. I need to have this. There may have been one in the room. Hopefully I didn't scout you out. But there's always someone who says, no. I have this very special case. I must be able to do this because then there's a very long and complicated explanation, which amounts to I don't want to do anything, and I just want the whole thing to keep working. And the system must provide that. And this is a problem. Usually these people are quite vocal. So then we have, from this, we can get the design principle number 3, is that the maintenance cost of anything should be borne mostly by those people who get the benefit from that. So in this case, if you have a system which forbids the use of like multiple versions of the same dependency, then everyone benefits from that automatically. And the people who have to pay extra cost are those who have these weird niche things. And then the thing of the theory is that, okay, you have a weird thing and very specific thing. And if we were to do this thing that you want, it would harm everyone else. You would get the benefit, and everyone else would pay the cost. And because of the Spock rule, we don't do that. So like, there's always ways to get around this. Maybe you can rename your thing internally or whatever. There's always a way around it. But the thing is that you do that because you are the thing that has the problem. And then you can do whatever it thinks. And this way, the benefit comes for most people most of the time. And as an aside from this, let's look at vendor releases. So this is a common thing, and some build systems do this automatically, where when you do releases, then what you have is a clump called a clump. So what happens is that the release thing, it takes all of the dependencies, all the source files, all the source code, and creates a single clump. And it's a vendor release. And the idea is that you give this out to people, then you compile this thing in isolation from all things, then you link against your thing. Usually these things are libraries for some functionality. So you compile it in isolation, you link the final A or .so file into your thing, and then everything works. And you're done. So this is what it looks like. So you have a main project, you have some dependency, it has a bunch of stuff, but you don't really care. Things are working as well. And this works for a while, but then your project gets a bit bigger. So then you take a different dependency, which is also a vendor release by someone. And it also has some internal things, but you don't really care about that. Except that now these two are the same. And it's hidden, so you don't actually know. So then you get ODR violation again. So the corollary of this thing is that vendoring works as a dependency method actually quite well if there is only one place in your entire dependency tree that does it. And even if it worked, so suppose you could have things, you still run the risk of building each dependency n times. So if you have 5 versions of Boost Spirit inside of your code base, you're probably not going to have a good time. Okay, so back into the actual content. So this thing that actually happens also is that during the lifetime of any project, you can be any one of these boxes. You might be a dependency that's fully isolated on its own, does one thing, provides a library interface, and everything is fine. It might be a library that uses other libraries and then provides something, or it might be a top-level project. And it could be in any one of those dependency boxes, and it moves from one to the other as the project goes along. So from this we get the design principle number 4, is that a project, when you write your build definition, then it must provide support for being a dependency provider or a dependency consumer. And it must work in a transparent manner, so you can just plug things in. Okay, going further. Now let's look at an example. So a typical combination of dependency management is like CMake and Conan. So I haven't used Conan myself all that much, so I copied this example from the internet. So typically what you would have is something like this. So you have a minimum version, then you have a project, and then you have an include a Conan build for CMake file, you call Conan basic setup, and then you do your thing. any link. And okay, this works. Okay, but suppose you want to use this thing from the sub. So this, let's assume that this is the build definition file as shipped by upstream. So suppose you want to use that as a subproject. Okay, you can do that. Build a source as part of your project. And suppose also that you want to get the dependency in some other way than Conan. You have some way of obtaining that. So what do you do then? So then the problem is that you need to edit the source code of the subproject to work within your project. And this is actually extra work that you need to do. And now you have delta to upstream. So the design principle 5 comes from this. Very simply, is that a build definition mustn't specify how a dependency is obtained. It mustn't specify from where it is obtained. It can have something like defaults, but it mustn't specify where it comes from, only what it is. And that is that you should be able to take any project and use it as a different subproject without any code changes, only configuration code. So nothing that's in revision control should be changed in order to be able to use that, because then you can just plug things from somewhere and drop them off to some other place. Okay, looking further, so here's a typical CMake snippet where you have your CMake CXX args and you want to add a flag to that. And again, this works. And if you do this as a sub-project, then you clobber the option settings in the master project. And in subsequent sub-projects that then go from there, but not the ones that were already processed. Maybe. I don't know. Does anyone know? Because the way variables work in CMake is very weird, and I never really actually understood it. So this is like a bit of a problem, because if you can change things that have already happened later by someone else you don't trust, or if you don't know what it does, it's a bit of a problem. So then you get, very simply, the design principle 6 is that when you process these subprojects, they must be configured and they must be built in isolated sandboxes and very narrow channels between them for communication. Again, so that you cannot change the state of especially the master project from a sub-project. But you need to be able to talk certain ways. More unfortunate facts of life going on from this is that not everybody uses your favorite build system. This is not really a problem for system dependencies, obviously. But if everyone used the thing that you like and it supported this, then you could just take them. But they don't. Let's look at how that would work. So as a simple case, if you use a C++ header-only library, you have an application that's compiled with Meson, say, and then you have a CMake subproject. This is actually quite simple, because what you actually want is the -i setting to tell you where the headers are. And then you can use that. And this is actually something that you can do. It works relatively well. But again, as you add more boxes, things get more complicated. So suppose you have your top-level project, it's built in Meson and uses a dependency in CMake, which internally uses a dependency also built with Meson. So how do you do that? You would need to serialize the state of all of Meson, like the settings, and feed it into CMake. And then CMake would need to, again, serialize it and feed it into the Meson invocation that it does. And you have the n-squared problem, because every system would need to understand about every other system. So if you do Meson subprojects, this happens automatically. It's not really a problem. You can do this with cross-build system. The package config provides a way, it's so-called uninstalled mode, where you have your build tree and you have your dependencies in there. And then when you do package config lookups, it actually returns those things. It's not very well supported. It's there. It works in some cases. But it's a bit of a difficult thing. So again, from this we get design principle 7. So we should try to support the simple cases of mixing build systems, because the benefit you get from that is just so big. Even though you can't really make it super reliable, usually it's not that big of a deal. So you might, this is the thing that there's actual benefit with that. But what you really do not want to do is try to solve the problem in the general case, because you wouldn't require cross-build system coordination. That's proven to be challenging, let's say. Okay, going further. So if we look at how you would obtain dependencies, being able to do this is great. You have your build tool, install, package name, and then it downloads things from the internet and things work. And this is really what you want for development, especially for non-Linux platforms where your system dependencies don't exist. This is the only way to do it. And this is what you want. It's totally fine. This is also exactly the thing that you do not want in some cases, because there are places where downloading dependencies automatically is prohibited. You have your legal department, and they have to approve every single dependency. Are you allowed to use this or not? And just downloading stuff from the net is problematic in this case, and you can't do that. So from this we get the design principle 8, is that there should be a centralized dependency downloader. It should be available, it should be there, but it should not be mandated. Like you should not say the only way to ever get dependencies with this system is to use this thing that we have, and that's the only thing that you can do, because it's not really scalable. And even further, companies really want to have their own dependency curated things, so make it easy to host your own. So in the case of Meson, if you want to host your own, it takes one web server and some files, and it just works mostly. But from all of these, so what is the most important thing? Collating all these things together, and the thing is actually cohesion. The more custom code you have in a build definition for any project, the harder it is to integrate with other projects. Because what tends to happen is that you get into the, I call the Jussi's law of programmers, which goes the following way. The problem with programmers is that if you give them the chance, they will start programming. And what this has happened several times is that people come to the Meson chat on Matrix and say, like, hey, I want to do this very complicated thing, and how do I do this? And then it's like, okay, so what problem are you trying to solve by doing this? And then they say the same thing again. It's like, no, I need to do this. And it's like, no. Why? Like, what is the thing that you're doing? And then they will tell you, okay, I have this, and then I want to achieve this. And it's like, oh, we have built-in functionality for that. And it's like, what? And this happens more often than I would like. And the thing is, programmers have a thing somehow in their soul, is that if they come up with a way to make something happen, that's what they want to do, instead of looking up. It's like, well, maybe there's something like an established way to already do this. So from this we get design principle number 0, because numbering begins at 0, and this is the most important one, is that you should solve the user's problems and do not provide them with a bucket of tools that they can use to code their own solution. If you are familiar with Bjarne Stroustrup's talks, one of the things which he mentions every often is that when he was designing C++, it was that if it can only do the things that he can come up with, then it's a failure. And for a programming language, this is a very good design principle. But the build system is not a general purpose programming. It's very specific. It does very specific, narrow thing. And what you want to do is that you solve the problems, you solve them once, have people use them, and then just ignore them. Okay, so what happens if we combine all of these things? And we need 3 things, obviously, because it's a good narrative thing to have, like, 3 things. And the first thing you need is a build system. And in this case, it's the Meson build system, which we're working on. So how do you look up dependencies? So you have like this. You have foo dep equals dependency foo. And the foo is the name. And this doesn't specify where it comes from or like how it works and so on. It's just, this is a thing that I need. And then the system goes off somewhere, looks it up in whatever way it can. And you can from the outside, you have command options on like telling how these things happen. And then you get back on an opaque object. It's like, okay, here's the thing, just use this where you need it. And then the second thing is that you need to have a dependency system. We have this. This is called wrap. And here's an example how you would use a different project directly from Git. So there's some bookkeeping information, but basically it's just at this URL, there's a Git repository, get that. And then when you run this, when you configure it, inside of that project is a variable called stb_dep. And take that and pass it as the return value. So when someone does dependency stb, and stb is a header-only project which doesn't do any releases, so you have to use it directly from Git, or you need to have your own checkout. And inside of that, we have our build definition, which basically says declare dependency and a bunch of stuff. So now we have separated what the dependency is from how it's obtained. And then we need thing number 3, which is the wrapdb. It's called. It's a web service for downloading dependencies. And the problem this is solving is 2 ways. First of all, is okay, we have this existing Meson project and we want people to use that. But again, as I said earlier, most dependencies you don't, because they have a different build system. So you can't do that. So then the interesting question is, like, what if they were usable? How would you make them usable? So this is the way we've done it, is that we take the original upstream source, and then you can submit Meson build definition for those projects. And then add it if needed. There's a web, it's done all by GitHub. And the thing is that then you get something like this. So this is the wrapdb file for zlib. And there's a bunch of things in here, but basically it says that here are the download URLs, all the checksums. And as you can tell, it's split in 2. So there's the original upstream source, completely unmodified, and then there's the patch URL for the things that you add on top. And for like legal compliance reasons, or like auditing purposes, this is exactly what you want, because like you can prove very easily, this is the upstream, and then this is the things that we added to it. You can give it out to lawyers or anyone, and they can, okay, we can do this. This is very clear. And you have completely separated out the original from the thing that you add on top. Right. And how you install, if you want to use from wrapdb, you do this Meson wrap install zlib, which is exactly what you would want. Right, so let's look at a practical example. So let's do a multi-platform game. It's in quotes because the actual game part is missing, but like you can get a window running, so that's 95% of the work, right? Game developer agrees. So let's use SFML for graphics. And then on top of that, we add the GUI. We're using Dear Im GUI, and there's a specific SFML wrapper library on top of that. On Linux, we use the system dependencies if they're available. And then if they're not available, then you just build. So the full build definition for this. So this is not demo code. This is the full build definition. Everything that you need to write yourself. You can actually, this is on GitHub if you want to get, I don't have a URL in this presentation, but it's under my personal pages. So basically you have a project which is SFML app and uses C++. Then you set a bunch of default options. These are not necessary, but they're kind of nice. And then you have your dependency. You need SFML, so you do a dependency lookup for SFML. Then you need the Im GUI library on top of that, so you look that up. Then you define an executable, which has one source file. And you need to specify that on Windows, it's a GUI application instead of a console application. and then you add the dependencies, which are the two. And this is it. This is all you need to write. And if you build it on Windows, so I didn't tempt the demo gods, sorry. So here's one I prepared earlier. So this is a screenshot. I built this on Windows. So there's the window, and then there's the ImGUI demo thing. And so there might be some of you wondering, it's like, okay, so but where's the actual code? This can't be that simple, right? Well, all the actual like deep work is here. So these are the wrap files for the dependencies that we use. So you see there's FLAC, FreeType for font rendering, libpng, ogvorbis, OpenAL, the 3D audio library that SFML uses, and a bunch of other things. And as you can tell, there's the package cache directory. That's where it downloads all the things. So when you start to compile, basically it just downloads all of those things, extracts them, adds the patches, and then build them as sub-projects. And it looks like as if they were part of your own project, even though they're not. And if you wanted to use system dependencies, you wouldn't need to do anything. You would just pick them up automatically. So in conclusion, the question was, in the presentation title, was like, how hard would it be? Somewhat hard, not massively hard. It's mostly just like laborious. There's been a lot of work put in this by lots of different people. I looked at the stats, and I think the number of different contributors to Meson is currently about 650 different people, which is like mind-blowing. But the good thing is that most of the work is done. So this is a thing that you can already use today. In fact, you have been able to use for like several years. But all the COVID isolation got people to polish all the different bits. So it's nice, and you can do that. And the future gets faster here if you contribute. So the biggest problem at the moment is that the number of packages on RapDB is a bit limited. But it's a thing you can farm out to people. And if you submit your own favorite things, then you can use them. So here's the website for more information about this, and open for questions. And there's a bonus incentive. So everyone who asks a question gets one of these mugs. These are unique. So there's only one batch ever made, and the only way you can get them is to ask me questions at conferences. So there's guaranteed to be worth at least like 10 million in the future. Currency not specified. I have about 10 of these, and I don't plan to bring in any of them back to airport security. So please ask questions and come talk to me later. Go ahead. Yes.
What would you say is the advantage of wrap over VC package?
So the question is, what's the advantage of wrap over VC package? I think VC package is very much tied to CMake. They do support some other things as well. The big thing is that you need, in addition to a build system, you need an additional thing, which is VC package, whereas in this you get all of the same like single binary, and you get all of this. I haven't used VC package personally all that much, so I don't know like the day-to-day details, but okay, so hosting your own, if you need to host your own, you have some files, you put them in your company internal web server, and that's it. And then you don't need anything else. And then you can just zip all of that, and you can, if you have reproducible builds, then you can just prove it. Okay, this is how you do that. Okay, but there you go.
Some things I was like, yeah, we do this VC package, we use VC package, with the like one half of the VC package is still behind CMake, nothing but like a lot of things right now can consume config files. So.
Right. So the point made was that the person here would use VC package currently because of various reasons. One more thing. These come straight from the factory and have been in a box at my house during the pandemic. So please wash them before you use them. Next question. In the back.
I would expect API compatibility being an issue, especially when you build dependencies independent of each other. Like, what if one of my dependencies deal with -dev short email or something?
Okay, so the comment made by the person here is that if you use pre-built binaries, like in the case of VC package, you might get ABI problems because if they're built with different flags than your main projects. Okay, so if you use like wrap thing, you build all of your source code in a single thing. So it's the same flags for all projects, unless the project does weird things, and you can't protect against that. But most projects don't. So the same caveats for ABI problems apply. If your dependencies are built with different flags, then you might have problems. You might not, but you might. Okay. So the question is, does it also run tests to handle this? Yes, we have a full test runner, and creates JUnit XML and supports gtest and all of the. It's a lot of code and does a lot of things. It's weird because like I no longer know all the things that it does because I just run the project. So there's lots of stuff. It's like I'm not really the best expert to answer. But yes. Testing cross-platform, and it does test automatically in parallel. You can tell it not to, and you can tell it to run tests in a loop until they fail. You can tell it to run tests in a loop under GDB until they fail, and all these things, life of usability improvements for quality of life. Yes, anyone else?
More a comment rather than a question regarding the principle type that you mentioned, that basically the packet manager should not change your build system, like file scripts and so on. I agree with that 100%, but Conan is not a good example here.
Okay, so the point was that Conan wasn't a good example in this case for the fact that you should be able to use things without changing the source. Is that okay? Okay. Okay, so it should be able to use this Conan in a way that doesn't require this. Okay, good. That's good to know. Again, I haven't used it all that much, so I don't know the details. For obvious reasons, I use something else. Okay, any other questions? There's still some mugs available.
Is having the build system and the package manager done together, all the benefits from there? For example, Corollary claims to be build system agnostic. Generators. But is the benefit from this?
Okay, so the benefit is the question is if I understood it, is that was like the benefit of having the build dependencies, dependency manager and the build system the same thing. Well, the thing is that then you get all of the things which are integrated. So if you want, for example, build your whole thing with ASAN, then you toggle one flag in Meson, and the same setting goes to all the sub-projects, and then it just happens. But if you have a different dependency downloader from a build system and you want to use ASAN binaries, then you would typically need to do something to make those ASAN binaries come from wherever they come from. Yeah. Anything else? Okay, so the question is, what's the impact of these on CI pipelines if you build everything from scratch? So there are two options for this. So you can use pre-built binaries if you have them. That's part of the design, is that you can either build your own, you can use existing ones if you want. The more important, like other thing is that if you are using, if you have a CI pipeline that's building something like C++ code and you're not using Ccache or SC cache, you are murdering polar bears. Don't do that. Like most large fraction of the CI problems go away when you have Ccache, because it's very rare that you need to change like the core bits. And if you don't change your dependencies, they always come from the cache. Only the code you change yourself has to recompile. So you can do it pretty fast.
Actually, talking about pre-built binaries, how does Meson add say I compile this with different compiler than I'm using now.
Okay, so the question is that how good is Meson at detecting that you build something with a different compiler than what you're using? For things that you compile yourself, it's always the same compiler. It's mandated you have one C++ compiler, and that's what you use for all your C++ code. For pre-built binaries, you can't tell. It's the information is not stored in the SO files in a reasonable way. So then you would that's a problem for you to solve, basically. Okay. Anything else? All right. Well, thank you for being here.